All right, so today I'm going to start really talking about developing detailed chemical kinetic models for hydrocarbon combustion. And probably a lot of today I'll spend talking about developing high temperature mechanisms. And then maybe tomorrow we'll talk about low temperature mechanisms. And then Friday maybe the mechanisms of oxygenated species as opposed to hydrocarbons. And how they're the same but different in ways, okay? So the first thing when we're developing detailed chemical kinetic mechanisms, we're not at the stage yet where you can just take a mechanism in isolation and put it together and then say, this will work against experimental data, okay? So what we do is we typically put a mechanism together. So if you take, for instance, there was a big effort, I don't know whether you're familiar with it or not, but there was a big effort by Bausch, Cobos, I think the people at Stanford were involved, David Golden, Michael Frank, a lot of people were involved in that effort in trying to come up with the best ray constants for the smaller molecule or species chemistry and atoms, okay? And if you took their recommended ray constants and put them all together, the mechanism actually wouldn't work, okay? And it's the same if any of us did the same thing, even though they're the best recommendations. So we have to actually validate the data against what's measured experimentally. And somebody, I don't know, was asking me either yesterday or the day before, well, what if there's 5% uncertainty in H plus O2 gives O plus OH? And you have so much uncertainty in this and so much uncertainty in that, and you've got 15% uncertainty in the experiments and so on. What do you do then? And I think that's why we have this discontinuity between the best ray constants that are recommended, and there are uncertainties of factors of 2 and so on, and what we actually observe experimentally in many cases, okay? So you have to be careful. And as I was showing you yesterday, the day before when we were talking about the propane oxidation, where we had a discontinuity between the shock tube data and the rapid compression machine data, there mostly the discrepancy came from understanding the limitations of the experiments, okay? So you have to take bear everything in mind when you're developing a mechanism. And fortunately, and this came up at the career advice thing yesterday at lunchtime, you know, you should try to be as diverse as possible. So I actually, when I was doing my PhD, I started off working with Professor John Simi in Galway, and I was doing shock tube ignition delay, measuring shock tube ignition delay experiments for isobutene. And then from that, I spent 3 months in Livermore working with Charlie Westbrook and Bill Pitts, putting a mechanism together to explain that. And then went back to Galway. And as a result of isobutene, then we looked at allene and propane, okay? So I have experience in both doing experiments and in modeling. And as an experimentalist, you think, oh, these experiments are perfect. There's nothing wrong with them. And when you come to the model, you say, well, the model is pretty good, and it must be the experiments that are wrong if the model doesn't agree with the experiments, and vice versa. But I think it's always best to keep an open mind on both. And what's best of all is if you have a lot of data available for you on a particular fuel, then you can come to conclusions. So the more experimental data that you have, the better in order to validate a chemical kinetic mechanism. Okay. So hence, we take as much data as we can from all the experimental facilities that are available to us. I've shown some here, the just stirred reactors. I spoke about flow reactors. We take flame speed data and also flame speciation data from flat flame burners, in addition to ignition delay times. Okay. So for chemical kinetic modeling, essentially what we're trying to do is understand how a fuel either pyrolysis or undergoes oxidation, typically in air, in a combustor, to generate carbon dioxide, and the energy, of course, is what people are after for combustion. Okay. So if we consider a small hydrocarbon fuel, the smallest one, which is methane, actually the mechanism involves 200 reactions and 30 chemical species to explain quite accurately methane oxidation in combustion environments. Okay? So, and the chemical mechanism involves both an understanding of the kinetics and the thermodynamics of all those species that are involved in the process. Okay, and so what I like to try and express or get across, if we picture, and when I'm explaining to my mom or my family, what is it I do? If you picture a fuel that's all together, like a giant jigsaw puzzle that's actually made at the very beginning, what we're trying to understand is, how does the fuel break apart? Okay, so does the fuel break in half? CC bond breaking or CO bond breaking? Does it break in quarters? Or does oxygen go in and take a hydrogen atom from the fuel and take it apart? And so we're trying to understand how all of this happens. And what defines or what determines how this happens are the chemical kinetics, the rate constants for the reactions, ultimately, as I said. Okay, and so the mechanisms are developed in a hierarchical way. And this slide that I'm going to, or this schematic I'm showing you is actually taken from an old paper by Charlie Westbrook and Fred Dreyer in 1984, where all hydrocarbon mechanisms are built in a hierarchical way, starting with the hydrogen-oxygen submechanism, then we have the CO, then the C1 species, carbon monoxide, formal radical, formaldehyde, and methanol. And then we have methane, which is closely associated with ethane, and then ethylene and acetylene, and then ethanol. And then above that, we have the C3, and then on up, C4, C5. So the mechanisms look a little bit like this. If we have hydrogen, we have a hydrogen mechanism involves 8 species and about 20 reactions. Okay? Methane, as I said, 30 species and 200 reactions. We skip ethane and go on to propane. It involves about 100 species and 400 reactions. So as we get bigger in carbon number, the mechanisms become more and more involved. Okay? And this is actually a slide taken from Bill Pitts, and I think actually maybe Elazar Ranzi was the first person to put it together. But it's sort of like the Russian doll model. You have hydrogen submechanism, then CO, all the way up maybe to a C16 fuel. Okay? And you want to develop the mechanism so that you have all the subspecies for the larger hydrocarbon species that are involved in the oxidation process. Okay. So here's just the title page of a paper that we published on syngas oxidation a few years ago from my group. And it just, overall for hydrogen oxidation, which is syngas is just hydrogen and CO, okay? The hydrogen oxidation mechanism, the overall reaction can be written as hydrogen plus a half O2 gives water, okay? But actually, it's quite complicated mechanism. It involves 20 reactions with all of these 8 species. We have reactions where we have a third body, and then we have efficiency factors for the colliders for different chaperone coefficients. Okay, and they're all provided in the mechanism. Yes?
What do you mean by
OH star?
yes, and
I'm asked, what do I mean by OH star? I don't see it, but anyway, OH star would be excited OH, chemically activated OH, okay, with excess energy. Okay. And this whole concept actually, probably, I showed you a schematic taken from a paper published by Charlie Westbrook and Fred Dreyer in 1984. But actually one of the first schematics of this kind was published by Jürgen Marnatz back in 1981, where he showed the mechanism for methane oxidation involving ethane and then ethylene and acetylene and so on. And you can see here the major pathways for propane oxidation. So propane oxidizes to give methyl radical. More modern one, I've taken it again from Professor Eliseo Ranzi from Milan. And this just shows you the main oxidation process for methane. So methane can undergo hydrogen atom abstraction. We form methyl radical. And then at high temperatures, that can react to give actually formaldehyde plus OH or methoxy radical. And then methoxy radical can decompose to give formaldehyde. Then that gives formal radical, it gives CO, and that oxidizes to CO2. Okay, at lower temperatures, methyl radical can add to molecular oxygen to give methyl peroxy radical that can form methyl hydrogen peroxide that gives methanol and then methylene hydroxide. Okay, so this is, we'd say, the oxidation mechanism for methane. Okay, however, we also have a pyrolysis mechanism. So instead of methyl radical undergoing attack by oxygenated species, it can recombine with itself to give ethane. And then ethane can undergo hydrogen atom abstraction, giving ethyl radical, which releases a hydrogen atom, giving you ethylene. This can give acetylene, and then through the Hacker process, which was published by Michael Frencklock and Hai Wang, can form aromatic species and lead to the formation of soot. Okay? And so this is the pyrolysis mechanism associated with methane. But also, with these mechanisms, we can also add other sub-mechanisms, including NOx. Okay? And so, but one, and also then other species as well, if you've got other SOx and so on, if you've sulfur oxides and so on. Okay, but if we look here, so the attack or the reaction of methyl with O2 dictates how much oxidation occurs. The self-reaction of methyl radical with itself dictates how much pyrolysis type reactions occur. Okay? So more than the correct rate parameters for specific reactions, okay, it is important to include all of the relevant reactions and the proper relative selectivity of parallel reaction paths. And I can't remember specifically what reaction it was. It might have been methyl plus HO2. I'll be showing that a little bit later. But anyway, Charlie Westbrook talks about how he and Fred Dreyer at one stage in one of the mechanisms that they had this important branching reaction. So this is just an example of one. I'm not sure if it's exactly the one that he talks about. But if we have methyl plus HO2 gives CH3O plus OH. Okay? That's chain branching. Or it's certainly, well, technically it's a propagation, but it leads to higher reactivity because methoxy radical gives you formaldehyde, which gives you formal radical, which gives you CO plus H. Okay? So you get two reactive radicals. You get H atom and you get OH radical from two relatively unreactive radicals, methyl and HO2. Okay? So this actually enhances reactivity in combustion processes. Okay? But if you have methyl plus HO2 giving methane plus O2, sorry, no radical. That's a termination reaction. Okay? And if you have the relative rates of those two reactions correct in your mechanism, then you probably predict the reactivity pretty well. But you may not have the absolute rates of the two reactions correct. But it didn't matter in the case. At least I think it was this reaction. And Charlie often talks about that. They were actually out by an order of magnitude in the absolute values of the rate constants. So sometimes the absolute value doesn't matter, but what does matter is the relative rate. Okay? Now, why am I going on about that? In developing mechanisms, and I'll show you as I go through the day today, that what we try to do, or what I try to do, and I would encourage you to do, is take rate constants that have been measured experimentally or calculated from high-level ab initio coupled cluster calculations. And probably the best people in the world at the moment doing that are Stephen Klippenstein and Larry Harding at Argonne National Labs. And so what I do is I take the highest level, the highest accurate rate constants, and I put them in the mechanism. Okay? And if we put an accurate rate constant for methyl plus HO2 into the mechanism, and then we don't have anything new, or we don't change methyl plus HO2, but if this had been out by an order of magnitude, now this other rate constant needs to be changed, or the mechanism won't work anymore. Okay? So is that telling you, so you have to then decide, well, is that telling you that the new calculation's wrong, or what we had before was wrong? So you have to make your decision based on the best knowledge that's available to you, and common sense. Okay? All right. Okay, so, and most of what I'm going to talk about today is in the small molecule kinetics, and each elementary reaction is treated individually. And extensive validation experiments usually exist, so many of the elementary reaction rates are rather idiosyncratic or unusual, and so they have a defined rate constant. What we're talking about there, if you look at calculations that are done for, we'd say, low temperature chemistry calculations where you've got an alkyl peroxy species isomerizing to a hydroperoxy alkyl species, work that's been done by Bill Green's group and Tony Dean's group, we'd say, here in the US. And they'll look at many different, we'd say, isomerizations of hydrogen atoms, which involve 5, 6, 7, and 8-membered rings, isomerizing primary, secondary, and tertiary hydrogen atoms. What they find in general is the rate constants are the same depending on the ring size. It doesn't really matter what kind of molecule it is. It really depends on the ring size and the type of H atom that's undergone abstraction. But for these small molecule chemistry, it's hard to draw analogies from one reaction to another. You have to take the rate constants that's being measured. Okay, but the principal reactions involved in most of the mechanisms are these two. And the primary one is actually this one here, H plus O2 giving you O plus OH. Okay, that's probably one of the most important reactions in combustion. Okay, followed by CO plus OH giving you CO2 plus H. Okay, so this slide is deliberately busy, right? And it's just we'd say, go back to this idea of how does the fuel decompose. And so we have this giant jigsaw puzzle. In this case, the jigsaw puzzle is ethanol. So how does ethanol undergo oxidation? Okay, so we have various different reactions that can occur for ethanol. Okay, it can undergo a molecular elimination reaction, producing ethylene and water. And this is the rate constant expression for that reaction. It can also undergo a CC bond cleavage, a CO bond cleavage, and then also another molecular elimination giving you acetaldehyde plus H2. Okay? It can undergo hydrogen atom abstraction reactions, typically forming, when it undergoes abstraction here by OH, it can abstract the terminal carbon atom, primary. So I label that the radical PC2H4OH. That's this radical here. Okay, PC2H4OH. And then S(C2H4OH) would be abstracting the secondary hydrogen atom, okay, on ethanol. Okay, and then you can also abstract the alkoxy hydrogen atom on ethanol. Okay, so you get 3 distinct radicals formed, and we have 3 distinct rate constants in each case, because the rate constant, the rate constant is different. The rate constant depends on the bond dissociation energy, the strength of the CH bond, or how strongly the hydrogen atom is bound to the atom that you're trying to remove, the H atom that you're trying to remove. Okay? And so, and there's lots more reactions that I haven't included in here. Okay? And then from the forward rate constant expression and from the thermochemistry, the code also calculates the reverse rate constant expression. Okay? So all of the reactions are allowed to be in equilibrium. Okay? It's retained. And so if we start off with ethanol then, and we allow the chemistry to evolve with time. Okay? So when we come to do a simulation, what is the simulation doing? How does it actually solve the chemistry? Possibly some of you are using them all the time, but maybe you haven't really thought about it. Okay? But what it does is it's very simple. So initially, if we have ethanol in air and it's going to undergo oxidation, what's going to happen in the very initial stages of reactivity? So if we put into the reactor, our combustor, we put ethanol, oxygen, and nitrogen, right? What can happen initially at the very start of reactivity? What can happen? Okay, but just simple, no chemistry. I'm talking chemistry now. I'm a chemist. No? Well, we have energy put in. Sorry, so you're saying you have to put energy in, but we have the energy available. So we're running the reactor at 1,000 or 1,100 Kelvin. We're at whatever pressure we're at, and the fuel and oxygen and nitrogen is there. So let's say we're burning ethanol in this E100 engine. It's all there. So before this goes, so it's there. We're just about to start up the engine. What has to happen for the car to move and for the engine to take over?
Either a CC.
Okay, so he said either a CC bond scission occurs or a CO bond scission occurs. Any other possibilities? H abstraction by oxygen. What about H abstraction by OH or H? If there's only oxygen in the fuel, then there's no H or OH to abstract. Okay? So at the very beginning, when the code is doing its computation of what happens experimentally, all that can happen is either the fuel can undergo one of these 4 reactions that we've included, or maybe other ones that we haven't thought about, right? And they're not included here, actually. And what about CH bond cleavage? So we could have C2H5OH giving us PC2H4 plus H, and C2H5OH giving us SC2H4 plus H, and C2H5OH giving us C2H5O plus H. They should also be included, and rate constants included for them in this mechanism. They're missing, right? They should be there, okay? But actually, and they should be there, okay? But in a lot of combustion conditions, as I said, the CH bond is so strong that it's only when you get over about 2,000 Kelvin that the activation energy barrier isn't as important anymore. And the frequency factor starts to dominate the rate constant. And they then start to compete with C bond cleavage and CO bond cleavage. Another point to remember is that OO bond cleavage, OO bonds are weaker than CO bonds, which are weaker than CC bonds, which are weaker than CH bonds. Okay? So in order of strength, CH are strongest, CC are next, CO are next, and then OO are relatively weaker. Okay? So you're quite right. So in this mechanism, when it comes to iterate the very first time step, okay, what it does is all that can happen are these 4 unimolecular decomposition reactions of the fuel and or its reaction with O2. So what it does is it takes a very, very small time step such that any one of the species that's present in the reactants only changes by a very, very small amount. I don't know what it is, but it's set at a very small amount. And the code, well, I used HCT, but I presume Chemkin is the same. You can limit the time step in the code, but it'll take as large a time step as it can, but within that allowable limit to what it can, how a species can change its concentration in that time step. All right? So it takes that time step, and now, after that very first time step that it has iterated, we now have the solution of the first calculation is input for the next one. So now we have mostly, again, fuel and oxygen, but we have a little bit of some of these products, whichever ones are dominating, and reaction with O2. And then the code takes another time step, and another one, and another one. Okay? And so, but what is telling, or what is dictating what happens to the fuel? Okay, so I didn't really ask that question very well. So in that first time step, then, which reaction is going to dominate of those 6? Or what determines which reaction will dominate? Pardon? Somebody said the smaller the EA, the Arrhenius numbers. Yes, but which Arrhenius number? Is it the A, the N, or the EA that's going to dictate? The combination of A, yeah, and N. Okay, all of it. So I didn't say it in my slides, but actually, a lot of the time, and you can see there, for most of these reactions, we have a T to the N, okay? It's because of some curvature. Oftentimes, when rate constants are measured, what happens is the rate constant as a function of temperature looks something like this. So if we have, that's very sideways now, okay? But if we look at rate constant as a function of temperature, it's not a straight line, there's strong temperature curvature. And in this case, it's strongly positive, okay? And you can see there that a lot of these reactions down here, there's strong positive temperature curvature. And typically for abstraction by methyl radicals, and in particular, and HO2, they show strong temperature curvature, okay? And so we have not an Arrhenius type of expression because this would be linear if we had Arrhenius type, okay? So what we have to do, well, I should have had 1 over T, I should say there. So what we have to do, where am I doing that, is express it as the K is equal to A T to the N EXP minus EA over RT, where we have this temperature curvature. And so effectively, the activation energy, the effective activation energy is changing with temperature, and it's curved. And so that allows for this temperature curvature to be included in the rate constant. Okay? So when we're considering, so what dictates whether this reaction or this reaction or this reaction dominates? Or, for this matter, these other two. It's the rate constant. Okay? So if we look, what is the rate of reaction 1 here? The rate of this first reaction is the rate constant times the concentration of ethanol. What's the rate of reaction 2? It's its rate constant times the concentration of ethanol. What's the rate of reaction 3? Its rate constant times the concentration of ethanol. So the relative rates are actually just the relative rate constants, because the concentration of the fuel cancels. All right? Now, it's not true, of course, when you come here, because then you're hit by the concentration of O2. This is bimolecular reaction. And we'll be talking about that tomorrow, certainly. Probably not later today, but tomorrow. So if we look at, we'd say, reaction 4, reaction 5, the rate of reaction 4 is equal to the rate constant for 4 times the concentration of ethanol. Okay? The rate of reaction 5 is the rate constant for reaction 5 times the concentration of ethanol times the concentration of O2. And if you look at the relative rate of reaction 4 over reaction 5 is going to be the rate constant reaction 4. I'm going to put a 4 here and a 5. Strictly speaking, from what I was saying yesterday, that's not correct. That should really tell you the order, not which, but just for this purpose. Okay? So the rate of reaction 4 is the rate constant for reaction 4. It depends on the rate constant for reaction 4. Sorry, if we look at the relative rates, the rate of reaction 4 over the rate of reaction 5 then is the rate constant for reactor 4 all over the rate constant for reaction 5 times the concentration of O2. Okay? So it'll depend then what the concentration of O2 is. But what is the concentration of O2? Say we have ethanol in air at 10 atmospheres. What's the concentration of O2 then at 1,000 Kelvin? Okay? How do we work that out? So we have P over RT is equal to N over V, which is concentration. So the partial pressure of O2 over RT will be the concentration of O2. Okay? So let's say the partial pressure, if you've got fuel in air, the partial pressure is about, or the fraction is about 20%. So you've got about 1/5. Okay? At 10 atmospheres, it's 1/5 of 10, which is 2, right? And 1,000 Kelvin, so it's 2 all over 2, which is 1 all over 1,000. So it's about 10 to the minus 3. Am I right in that?
That's if the 10...
Oh no, this is 100, 82.06, sorry?
That's if the 10...
That's if the 10 atmospheres is air, is everything. Well, it's the whole mixture, okay, at 10 atmospheres. So I should say the partial pressure is going to be then, it's going to be 2, and it's just an approximation. We're not going to worry about that. 2, or actually in this case, because if this is in atmospheres, it should be 82.06 or something like that. So let's say it's about 100, okay? So it's about 100 times 1,000. So it's 2 times 10 to the minus 5, about. Okay? So this bimolecular reaction, if we have oxygen in there, this concentration is going to reduce this rate by 5 orders of magnitude. Okay? But what is the relative rate constant then? Is this much higher than this, or is it lower than this? Now, we'll be talking about this tomorrow when it comes to low temperature chemistry. This is very important, where the low temperature chemistry stops and where high temperature chemistry comes in. Okay? But here, so what's then going, but my point is this: what determines really what's produced in that first step is the relative rate constant, is the rate constant of each reaction, okay? There's nothing we can do to control the concentrations of ethanol. Well, there is, but once we have the concentration, that's it, okay? That's not changing for each reaction. The concentration of ethanol is what it is. The concentration of O2 is what it is, okay? So typically, initial stages, we have unimolecular decomposition or we have abstraction by O2. And if you look at these and you iterate these, what we find is, particularly at lower temperatures, this unimolecular decomposition reaction typically dominates. And we get ethylene plus water produced, okay? And then we iterate again the next time step. And we have a little bit of ethylene now, okay? So now ethylene can undergo unimolecular decomposition. Okay, that'll happen at a very small rate, but it will happen. And then O2 can react with ethylene to produce vinyl plus HO2. Okay? And then we iterate again and again and again and again. And eventually, the system will auto-ignite or it'll reach a steady state or whatever type of simulation you're doing will finish. And you can compare what the model then predicts is produced against experiment. And that's the value of the experiments. So say you have these rate constants in there, and lo and behold, you find actually in the experiment you see a lot of acetaldehyde and no ethylene. Then your rate constant for the formation of ethylene plus HO2 relative to that of acetaldehyde plus H2 are wrong. Okay? Maybe both are wrong. Maybe one's too fast relative to the other, or whatever. But that relative rate is telling you is wrong. Or the absolute rates are wrong. But there's something wrong, okay? But if everything agrees, then your mechanism predicts this set of data pretty well, okay? But that's one set of data, okay? So you need then another set of data, like ignition delay times or something, to predict, okay? And then you need flame speed and so on to predict. And then when you've got lots of data sets for which this mechanism performs pretty well, you have more and more confidence that the mechanisms, the rate constants in your mechanism are correct. Okay? But I hope you can see clearly now that it's the rate constants that you're after. It's all about the rate constants and having the reactions in there. Yes? Yes. So I was asked, is this sequence consistent for all the fuels? And the answer is yes. So there are some automatic mechanism generators now where you use the rate rules that I'm going to show you over the next few days to generate mechanisms. But particularly, I think that was one of the main advantages or selling points, or I don't know, of the N-heptane and isooctane papers that I published with Charlie and Bill when I was in Livermore, was the fact that we detailed how we put the mechanism together. So we have reaction class 1, unimolecular decomposition. Reaction class 2, hydrogen atom abstraction. Reaction class 3, daughter radical beta scission. Reaction class 4, whatever it is. Okay? And so there is a template there for how you put a mechanism together. You have the fuel, unimolecular decomposition reactions, reactions with O2 and other radicals, then beta scission of the daughter radicals and so on. Yeah. Yes?
So let's
Yes.
So each species has the reaction rate.
I don't think it'll affect the CFD. So I was asked, how will if you're combining CFD and kinetics, how will it affect it? It affects it in terms of the heat release that's given out by the species, how the chemistry is evolving. So again, the kinetics evolves the chemistry, and that predicts the heat or produces the heat release or not within the process and so on. And that will then affect your CFD back. Now, one thing you'll see later today, that actually in a lot of these transport involved problems like CFD, most of the transport involves hydrogen atom. Certainly for flame speeds and flame, burner flame, stabilized burners, H atom is all important. Because it's just so light, it can be transported from the post-reaction zone back to the pre-reaction zone and contributes to fuel oxidation in a major way, okay? And I'll talk about that. I have deliberately, so don't worry about all the details on this slide or whatever. The idea of this slide is just to show you, look, it is very involved. The code is going to calculate every one of these reactions. But at the very beginning, the only thing that really can happen is unimolecular decomposition or reaction with O2. And what really determines what's going to happen in the next time step is what's the relative rates of these in the first place and what's produced in that first time step. And it iterates through each time step without any species increasing by a set amount, which is very, very small, okay? So that we don't lose any of the chemical detail, okay? So there are a large number of reactions and combustion mechanisms, and often direct experimental determination is difficult over a wide range of temperature and pressure. There's few experimental data with a limit, and it's limited to light species. It's just saying what I said again. So we have estimation methods, we have collision theory, as I showed you yesterday. We have correlations between structure and reactivity correlations. We have linear free energy relationships, such as Evans-Polyani. I hope I have an example of that. And methods based on transition state theory and quantum calculations. And more, we're using quantum chemistry calculations to guide us in terms of the rate constants for a reaction. Okay, there's online databases. If you go to the NIST Chemical Kinetics database, that's available. I spoke about the Balch, Bowman, Cobos. There were a series of releases of recommendations that they had through the 90s and 2000s, I think. And then Wing Zhang has published a lot of recommendations in Journal of Phys Chem reference data back in the 80s and 90s, which I still use a lot, actually. And then there's lots of online mechanisms available. I haven't included the KAUST here. This is a little bit old, but we have CloudFlame now from KAUST also. But this is just showing you there's lots available. But one thing, and this isn't, yes, it's the Galway site, but it's not trying to plug the Galway site. There's a particular address here, links.html. There's lots of links to combustion groups and so on there. And if you're trying to find something fairly quickly, it might be a good sort of one-stop shop. I'm not saying it's one-stop, but it might be a good route to where you want to, what information you're looking for. Okay, so let's try and get into a little bit more involved. I'm taking it slowly, but I hope it's worthwhile. If we look then, I'm going to talk today, as I said, about the smaller hydrocarbon species. And there's a reason for that, because if we look, here's a sensitivity analysis, and I could do this for any fuel. This just happens to be methylbutanoate, and I took it from a work that Stephen Dooley published with us in 2008. But it could be any fuel at low pressure and high temperature. So when I say this is at 1 atmosphere and 1300 to 1600 Kelvin. And we see here, what are the important reactions? Enhancing reactivity if the bar goes to the left, or decreasing reactivity if you go to the right. Okay? And you can see that most of the reactions, I've highlighted them here sort of in a yellow, are involve low, smaller species. H plus O2 gives O plus OH as by far the highest bar. And you'll see this all the time when you're developing mechanisms that have strong high bars. Okay? This other reactions that I was talking about a little bit earlier, methyl plus HO2 given methoxy plus OH. If we increase, this sensitivity analysis is performed by increasing the rate constant by a factor of 2, both forward and reverse, and seeing what effect that has on the predicted ignition delay time. Okay? And you can see the most important reaction then, inhibiting reactivity, is methyl plus HO2 giving methane plus O2, because it competes with this reaction, enhancing reactivity. Okay? And then other ones, vinyl plus O2 is very important. Ethylene plus any radical giving vinyl plus any stable species is very important. Formaldehyde reactivity is very important. And again, some other reactions involved in the hydrogen chemistry and the C1 chemistry all show to be important. There's only a few reactions, fuel decomposition under these conditions, particularly at 1300 Kelvin, tends to be important. Okay? And then fuel reaction with radicals tend to inhibit reactivity here. And if you look at it actually, if we look at fuel plus methyl, that seems to promote reaction, particularly at 1300 Kelvin. But fuel plus H atom inhibits reactivity at both 1300 and 1600 Kelvin. Why is that? Why would fuel plus H inhibit reactivity at both temperatures? Because surely if you increase the rate of that reaction, it'll consume more fuel and you'll have more reactivity. So it doesn't seem to make sense that it inhibits. Okay? And again, the answer is very simple, because this reaction will compete with H plus O2. So remember, at the start we have fuel and oxygen. Okay? And if we generate lots of H atoms, which happens, okay, they can either react with the fuel or react with O2. If H reacts with O2, we get the most important reaction in combustion, the most important chain branching reaction in combustion. But if H atom, the fuel competes for H atoms with O2, then that important chain branching reaction doesn't occur, or it occurs at a lower rate, and hence the reactivity decreases. Okay? So it's sort of counterintuitive. All right? So, but it's telling you here that it's decreasing reactivity. Okay. But the main message here is that it's hydrogen, oxygen, C1, and maybe some ethylene chemistry that's controlling reactivity at this condition, along with some of the fuel, the main fuel. But there's very few intermediate species involved. Okay? So to develop a mechanism then, okay, what we've done in Go, we've developed a mechanism for hydrogen CO, and then the C1 and oxygenated C1 species. So, and we take measured ab initio rate constants where possible, and validate over a wide range of conditions. So what you want to do for any mechanism, these ticks, I think we have more, but anyway, it doesn't matter. It's just showing you, look, for any fuel, what you want to do is validate against as much data as possible. So here we have shock tubes, jet stirred reactor, flow reactors, flame speed, flame speciation. We could have rapid compression machine data also. And over a wide range of temperature, pressure, and equivalence ratio. Okay. Okay. And if we just focus, the focus in combustion is really on three distinct chain branching pathways. At high temperature, H plus O2 gives O plus OH is the dominant branching reaction. Okay? At intermediate temperature, H atom reacts with O2 and a third body to form hydroperoxy radical. And then that hydroperoxy radical can react with a stable species to give a radical plus hydrogen peroxide. And then hydrogen peroxide can decompose to give 2 hydroxy radicals in a chain branching reaction. Okay? So at intermediate temperature, this is the important sequence of reactions that occur. Okay? There is another one actually that I'll discuss tomorrow. Okay? And at low temperature then, fuel radical reacts with O2 to give alkyl peroxy radical. Then the alkyl peroxy radical can undergo an internal isomerization to give hydroperoxy alkyl radical that can add to molecular oxygen again, giving a peroxy hydroperoxy alkyl radical. And then that can ultimately decompose to give an alkoxy radical and 2 reactive hydroxy radicals. Okay? The point of this is, though, in this sequence, we'll be talking about this tomorrow, you get, if you have fuel in your present, you get a relative concentration of fuel radicals, and the concentration of fuel radicals leads to the formation of 3 reactive radicals, and we get chain branching. Okay? And I'll mention this tomorrow, or I'll show it tomorrow, but at low temperature, what we find then is that fuel-rich mixtures are faster to ignite than fuel-lean mixtures. Okay? Because the reactivity is depending on the concentration of fuel radical. And the fuel radical depends on the concentration of the fuel. So if you're fuel-rich, more fuel, more reactivity. So at lower temperatures, we see that rich mixtures are faster to ignite relative to lean mixtures. Okay? At high temperature, the opposite is true. At high temperature, lean mixtures are faster to ignite than rich mixtures. So at high temperatures, you have lots of H atoms in the mixture, are produced from the fuel. That isn't rate limiting. What is rate limiting at high temperature is the concentration of O2. And the higher the concentration of O2, the more reactive your system is, because the rate of this reaction becomes faster and faster due to the concentration of O2. Okay? So at high temperatures, lean mixtures are faster. Okay? And actually, at intermediate temperatures, rich mixtures are faster too. So at intermediate temperatures, lean mixtures are faster too. Okay? Now, that's kind of strange but true. Okay? What happens? Yes, we do get H plus O2, and there's a combination of these 2 factors. We get quite a lot of HO2 radical formed in the NTC region, okay, of the oxidation process, okay? And it takes some activation energy, so HO2 then goes on and reacts with fuel to give the radical plus H2O2. Now, it takes some activation energy barrier then, about 40 to 43 kilocalories per mole, to break this OO bond, okay? And at low temperatures, we'd say 600, 700 Kelvin, that's not easy to overcome. But when you get to 800, 850, it's easier to overcome that. And now the OO bond starts to break, and we get lots of OH radicals, okay? So because we're getting more HO2 in the intermediate regime, we get more OH radicals. And eventually, above 850, then the system becomes fast again, okay? We're rolling over. But that still doesn't explain entirely why rich mixtures are faster. Well, one reason is because we get a higher rate of reaction. If we have a higher concentration of fuel, then the rate of this reaction is faster, okay? That's one reason, okay? But another reason is because when we get the fuel radical, still at intermediate temperatures, and I'm talking about intermediate temperatures now, maybe 900, 1,000, 1,100 Kelvin, right? You still get the alkyl radical adding to molecular oxygen, giving you RO2. But not depicted on this slide is the molecular elimination reaction of RO2 giving you an olefin, the hydroperoxy alkyl radical, QOH, plus HO2, okay? So there's another reaction at intermediate temperature where this fuel radical still adds to molecular oxygen given RO2, but mostly then this species goes on to produce a hydroperoxy alkyl radical and HO2. Okay, so you're getting more HO2. So the concentration of HO2 then is stemming in that sequence from fuel radical concentration again. The higher the fuel radical concentration, the higher the concentration of HO2 will be, and therefore the faster the reactivity will be, because we're going to get lots of OH radicals to consume the fuel. Okay? And I know I'm introducing it now, but I'll be going on about that mostly tomorrow. Okay? Yes? Yes, but I will do that tomorrow. Okay? So I was asked, can I explain the transition across the NTC region between these three reaction pathways? And the answer is yes, but tomorrow. Okay. I don't know what's going on here. It's probably a good time to take a break anyway. Okay, and we start again at 10.